Problem 6.89 from mastering, and we have this frame given in this figure. We're looking for the x and y components of the force which pin C exerts on member ABC using scalar notation. The F1 is given here, which is applied, so this is very important. Please notice that F1, you may have a different number here, but it's a given force. It's applied to the pin. Okay, F1 is applied to the pin C. Is not applied directly to member ABC or directly to member EDC, but it's applied to the pin. So keep that in mind first. Since we are looking for the CX and CY exerted on ABC, on this member ABC, and by the pin C. So to find the forces between the member ABC and this pin C, we have to separate them, right? Because only when we separate them, then we can show the CX and CY, which are the forces applied on the member ABC by pin C. So that's the very direct approach, which is to draw the free body diagram of the member ABC by removing the pin C, but only leave the reactions or the forces exerted by pin C. So this will be the kind of the analysis to find or to expose CX-CY on ABC. We need to remove pin C from ABC and draw the free body diagram of ABC. So this is ABC, and start from point A. Point A, there is a rocker, so there will be one support reaction at point A, which is based on the XY coordinates. I'm going to set this as a positive X reaction. So there's only one X reaction, which is perpendicular to the vertical supporting surface. So this will be, I'm going to call this A of X. And there's no AY. And at point B, there's a pin, right, connecting the member ABC and member DBF. When we remove this pin B to separate member ABC and the DBF, there will be two reactions left on this member ABC, which are BX and B of Y. Alright, so this is the first time we're showing those unknown forces, so it doesn't matter which direction you put them, but just keep them consistent for the next free body diagram if you're going to show a reaction of this pair. Okay, for now, both of the forces, I assume they are in the positive directions. And then will be the forces CX and CY, which are the forces we're looking for, CX and CY. All right, apparently there are a total of 5 unknowns, right? And we can only write 3 equations. So we do not have enough equations to solve all of the unknowns. That means we probably need to draw other free body diagrams to solve some forces first, and then to solve the ones we're looking for. So usually, right, you probably cannot solve CX and CY directly. If you can do that, then there's no need to draw this free body diagram. So that means we probably need to find AX first, BX, BY first, and then you can solve CX and CY. That's probably the approach. Now to find AX, that's actually simple, because if you take the entire truss or entire frame, okay, so let me finish this. I didn't put this is the free body diagram of the member ABC. And next, if you take a look at the entire frame, again, when we check the entire frame, everything, okay, the pins are left on them. So the forces at B, at D, at C will be internal forces. Okay, we only look at the outlines of this entire frame. We only remove the support here and support here, and so for the entire truss, there will be one support reaction. There's an AX applied at the rocker, point A, and then there is a pin support at point E, so there will be two support reactions, right? EX and EY. So I'm just gonna keep it simple. This is the free body diagram of entire frame. That's it. We do have the applied forces. One is at point F, that's a 300 Newton. One is applied at point C. Again, doesn't matter if it's applied to the pin or if it's applied to the frames, because all of them are part of the entire frame. So this F1 is applied to the frame, okay, to the whole thing. Therefore, those are the two applied forces. For the unknowns, how many do I have? 1, 2, 3, right? 3 unknowns. But do we need to solve all of the unknowns? For now, I think probably we don't, okay? So, from the free body diagram of the entire frame, we can solve AX. All right. After we solve the A of X from the entire frame, we can say, okay, this is now it's solved. We reduced the number of unknowns from 5 now to 4. But still, we do not have enough equations. We only have 3 equations. We have to take care of one more force and to reduce the number of unknowns to 3. Which one should we take care of next? Again, CX and CY probably are not one of the choices because those are the last pair we can solve, right? So the other pair we can take a look at will be the forces applied at pin B, BX and BY. If we can solve one of those, BX or BY, from another free body diagram, then we can solve the rest of the 3 forces. All right, so the pin B, right, connecting member ABC and member D and F. So another pair or the reactions will be applied to this member, adjacent member, DBF. So let's draw the free body diagram of the member DBF. So let's start from the top, which is pin D. So when we take this member DB off away from the entire truss member or entire, entire frame, we need to take off the pin D, we need to take off pin B, but we need to leave these reactions there. So at pin D, there are 2 reactions, D of X and D of Y. So again, this is the first time we show those reactions applied at pin D, so you can just assume they are both in positive X and Y directions, okay, to make it simple. And now at pin B, we know that at pin B connecting member ABC and member DBF, so the reactions or the forces applied by pin B on those members are action and reactions. So that means this is the B of X applied to ABC is the action, or this force applied on DBF will be the reaction of the force applied on ABC. So same magnitude and opposite direction. So this is the B of X applied on member DBF by this pin B. So this is a pair of action and reaction. Same idea, the B of X applied on DBF is the reaction of the B of y applied on A, B, and C. So this is the B of y and is the action and reaction as well. All right, so that's at pin B, at point B. And point F, there is an applied force, which is to the negative y direction. All right, let's see. Our goal is to solve bx or by. So dx and dy, can you solve it? Maybe, but do we need it? Or do we need them? Well, I will say no, we do not need them. We only need to solve one of those, right? Bx or by. Can we solve any of those? If we don't care of the forces applied at pin D, at point D, how about we take the moment about point D? So just do a quick scratch. Moment about point D equal to 0. Now dx dy will not show up in this equation, and by actually passes through point D as well. Therefore, by is not appearing in this moment equation as well. So the only forces that you will see in this equation will be bx and the 300 Newton force. And looks like that the moment arm is kind of, I'm just gonna keep it simple, okay? So it's negative bx times the moment arm, which is db, then minus 300 Newton times the moment arm, which is df, equals to 0. And db is half of df. So you're gonna do the calculation, but you can solve bx from this equation or from the free body diagram of dbf, right? This can be solved now. After b of x is solved, now you go back to the free body diagram of ABC. We have how many left? 3 left, right? Cx, cy, and by left. There are 3 unknowns after you draw the free body diagram of the entire frame and free body diagram of the member dbf. We only have 3 unknowns on the free body diagram of ABC. Then use the 3 equations you can find from the free body diagram of ABC to solve all 3 or to solve only Cx and Cy, and this problem is solved. So the strategy for solving the frames and machines is, well, first start from one free body diagram that is kind of the most closely related to the unknown forces. In this case, is the free body diagram of the member ABC, because we are looking for Cx and Cy. And then check the number of unknowns. If we do not have, or if the number of unknowns are more than 3, then we're going to think about how do we reduce the number of unknowns to 3 by using actual free body diagrams. I think one thing that really confuses us is here at pin C, should we put F1? Should we place F1 when we draw the free body diagram of the member ABC? Some of you probably put F1 here and then ended up to have a wrong answer. Well, why do I not have F1 here? Is because, again, we are looking for the forces exerted by pin C on member ABC. So to find that, we have to take member ABC, or we have to take pin C away from member ABC. We have to separate them to show the forces exerted by pin C on member ABC. So when we took the pin C away from member ABC, remember F1 is applied on pin C. So when you took pin C away, F1 is took away as well. Well, you may say, why is that? Why do I take pin C away? The force is gone as well. Well, think about the member dBF as well. On the member dBF, when you took member ABC and dBF apart, well, there's a force F1, which is 300 Newton applied on the member dBF. Did you leave that force on member ABC? since 300 is applied to the entire member, why don't you leave 300 Newton on member ABC? Well, because it's not applied on member ABC directly, it's applied on member DBF. So when you separate member ABC and DBF, that force is not left on ABC. It's gone with DBF. Same idea for the pin C. When we took away the pin C, the force applied on pin C will be gone as well. Will not be applied directly on ABC. Well, this force does have effect on the forces of ABC. CX and CY is different because of the F1. If you do not have an F1 force on the pin C, the CX and CY will have a different value, will be a different value than when you have an F1 applied on the pin C. So to summarize, the F1 does affect the forces applied on the ABC indirectly. Even if you don't have it draw on the free body diagram of ABC, it does affect the force. But again, it's indirectly affected. So do not put F1 directly on member ABC.